All right, so we're back. So I guess it's time for me to start, and welcome to my session today. So basically, what I'm going to do today is take you through a journey of mine where I actually ended up building a distributed 3D render farm using some cool tech like Camel-Quarkus and Artemis. So just a few words about me. I'm a specialist solution architect here at Red Hat. And usually I travel throughout EMEA to deliver POCs and workshops to customers. So, but since the pandemic, I still stayed at home and did all the things from home. And so I'm part of a specialist team where we focus on event-driven systems, on integration. So everything that's related to Camel, Kafka, Artemis brokers, and things like that. I deal with those on an everyday basis. And so when I'm not doing that, I'm pretty passionate about indie filmmaking, but specifically with cheap gear and like vintage lenses. So it's something quite particular. And in the last few years, I did a lot of home renovations. So my wife and I actually bought up a few old homes and then we renovated them in order to rent them out. And the thing is, last year we actually built our house. So we had construction contract and we were able to build a house from the ground up. And so came the challenge to actually do interior design because this will be the home that that we'll be living in for quite some time from now on. So the motivation was that I didn't want to make any wrong decisions when it comes to interior design, right? So I really want to avoid to be in the situations where my home would look something like this. That would not be good, and my wife would not be happy for because of that, right? What did I actually do in order to solve this issue? So I thought to myself, there's this software that I used to use since 2005, actually, to do some 3D films, cartoon films at the time, in my spare time. And so this software is called Blender. I actually picked it up again and I saw that it evolved tremendously. And you could actually use this to do some archviz, right? So interior design visualization. Could model your home and then you do a photorealistic rendering. So I picked it up and I was having this idea of just simulating the different designs that we could have in our home. And I didn't want to pay a real architect for that because it's out of our budget, right? And so I actually managed to do it. So this is an example result that I was able to produce of our living room and kitchen. And maybe I'll just show you the Blender interface itself. If I can get it. Right. So this is the 3D model that I ended up building. And so we can go ahead and choose a camera and then just start rendering one of those views. So this is a picture that I pre-rendered, and this is sort of the result that you could get out of it. So pretty interesting, right? So let's get back here to my presentation. So I was very happy because I could, simulate some of the things that we were not decisive on, like choosing the material of certain furnitures and certain things. So this really helped us, make a good decision, and before going on and buy things and regretting it afterwards, we could simulate, changes of materials and colors to see how it would look like. But there was a catch, actually. And it was simply the fact that these photorealistic renderings, they took a lot of time. So if you actually wanted to have a full um, HD resolution rendering, was pretty painful. So, for example, here you can see that one of these rendering takes up to 40 minutes to have a result, right? And that was simply unacceptable for our artistic choices because we couldn't wait, 30 minutes to see how a certain color would affect the final result. So this was kind of a deal breaker of using this method to come to an agreement. So the challenges were we needed to have faster render times, and it should be using quite cheap, resources. So essentially commodity resources. It should be able to run on old computers that we have lying around. And I was actually able to leverage those because I installed them on the machines. Actually confiscated all of the computers in the house and then started just rendering day and night. And it was good. So how did I actually do this? You see, the pictures when they render, you could actually divide them into tiles. So it's a problem that is divisible, and so can process things in parallel. So the idea is to divide the picture into different tiles and then distribute that calculation over several compute nodes, right? So you might think that there must be some software out there that already does that. So I actually looked it up, but it wasn't. There was nothing available to do the specific thing that I wanted to do here, which means rendering a single picture but in parallel. So usually, what is out there in the open source world and around Blender, you could only find engines that would render an animation, so it would distribute different frames, but not a very complex frame cut into pieces and then rendered. So that led me to actually build my own rendering engine. And so I thought to myself, I work in distributed architecture. I know distributed architecture very well, so maybe that can come in handy, right? So I was thinking about the logical architecture that this thing should have, and we should, have a browser where we could upload these blend files, models, and rendering instructions. And basically through this browser we would push the file to a broker, sort of broker, through a topic that should broadcast the file towards various rendering units, right? So several rendering engines. Then, once these units have acquired the file, we should be able to send out rendered jobs to say, okay, you are responsible for rendering this tile, and you would be responsible for the next one, and so on and so forth. And so this would be done in a queue, right? And then these render engines would then consume messages from this queue and then render the different tiles one by one, but in parallel. And then the results, I would expect them to return through a queue to the component and then show up in the browser. So this is the logical architecture that I was thinking about. And then came the question of, so what should I use, right? And I ended up choosing the Apache Artemis broker. So at Red Hat, we actually have a product for that. It's called the AMQ broker. And for the services that would orchestrate the actions on top of the Blender engine, I would use Camel on Quarkus. And so I created just a unique component where you could connect to it through a browser. You could actually connect to any of those instances through a browser. They are all of them are identical, right? And there's no master. They're just everyone is identical and is able to communicate with each other through the Artemis broker. And so what this what we could do then is then through this browser, we could push a blend file through it, and this blend file is published through the broker to the other instances. And then we could queue up the jobs, and then these render instances would then start doing their job as they should. And so there was a question that I had, like, why did I actually use the ActiveMQ Artemis? So we needed, I needed an asynchronous communication possibility between the different engines. So that was the first requirement. H- Historic events and replays is not a hard requirement here, right? So if we think about things like Kafka, it wasn't really required for this use case. But what actually was the main choice, the main reason I chose Artemis is because it is actually able to handle large payloads, right? So these blend files, they could go up to like 400 megabytes or so. The one that I will be using in the demo today is actually around 70 megabytes. So that's a huge workload if you see it in terms of messages to be vehiculed through the messaging infrastructure. And so things like Kafka are actually not suited for those. And there's only one broker that I know of out there, which is Artemis, that actually supports large payloads like this natively. And so you can actually stream these large files, and they would be, transferred by chunks in order to avoid unhealthy, excessive memory usage. And also, I chose this because it's very easy to run anywhere. Could be on a local VM, it could be on a bare metal, and could also be run in containers in the cloud. Um, and so then the next piece is, why did I choose Apache Camel and Quarkus in that situation? So Camel is an integration framework. Um, it offers around 200 connectors and patterns that you can reuse very easily to build your integrations. And so, just for simplicity, it was very convenient to be used in here in order to orchestrate, all of the operations between the events that are coming through ActiveMQ and the Blender engine. Also, it's capable of streaming large files, and it's also capable of connecting to WebSockets to communicate with the browser. So you can see events happening in real time in the browser, which adds to a nicer user experience. And also it supports JMS in order to communicate with ActiveMQ here. And then, so Camel actually comes in different flavors. So you can actually use Camel as a standalone. You can use it on Spring Boot. There's also Camel K flavor, that's Knative. But Camel-Quarkus is something that was very interesting in this use case because, well, first, it's very suitable to containerized workloads. And so if we want to put this on containers, it would be very, very easy. And the quick boot times gives it a very nice potential to be used in like serverless and Knative environments. So you had a presentation right before this about a little bit about Knative. Basically, it allows you to scale down to 0 and then actually provisioning resources only when there are messages there, that when there are requests there, and that is something that's economically very, very interesting. Right? So if we zoom in into the component, Camel-Quarkus, this is mainly the different actions that it covers. So as inputs, we have mainly the rendering requests, right? And as output, then as actions, we would then actually download the file locally, open the file, launch renders, and then send the rendered tiles back to the engine that actually asks for the renders. So this is basically the different actions that it covers. If we go further, I'm just going to show you a quick demo of what it looks like. So this is the project that I've built. And this is really the core of what the render engine is actually. Contains a bunch of routes that wires the messaging infrastructure to the Blender engine. So you can see, for example, here, if I'm launching a command to open a blend file, it actually calls the Blender the Blender API in order to open it, and then it also sends some notification to the browser through this wiretap here. So notify opened to the browser in order for us to see that everything's working fine. Okay, so I do have an OpenShift environment for today's demo. I was not going to run it locally because it would stutter probably the presentation. So I actually provisioned an OpenShift cluster with some resources, and I already installed the Artemis broker right here. Right. So now let's go ahead and deploy this component. So I've actually already built it, and we shall just go ahead and deploy it. So deploy. This is my deployment file. What's important in here, let's just start with deploying like one replica and see how it goes from there. So let's go OC apply. So it has created the deployment. It has created all of the routes and things to access our app. And so if we look at the logs, it's up and running. Happy with that. And this is what the interface looks like, right? So let's go ahead and actually upload a file to this server. So I'm going to upload the file through a bastion. I could do it in here, but my internet connection is not so strong, and uploading a 70 megabyte file is a bit long. So I'm just going to do it from a bastion, and you'll actually see that even though this happens remotely, I'll see some updates on the browser, which is very nice. Right? So just reconnect to this. So here I have this blend file. It's about 80 megabytes big, and I'm just going to upload it with a curl command. So you can see it's uploaded, right? So it says here, this render instance is up and running, and it has received it. Now we can actually send an open command to open this file here. And so now it says, this engine has opened it successfully. And here we can actually run a render. So to explain very quickly, the parameters for rendering, what's important is the resolution. And then there's this samples configurations here. So Blender is a ray tracer. The more samples you give it, the more it launches rays of light. It's simulating rays of light in order to get the rendering done. So the more samples we have, the nicer the image looks like, but the more costly it is in terms of compute, right? So let's just run a smoke test and then see what's going on. So you can see here. So since we only have one engine, it's rendering one tile after the other. And we can see down here that the image is coming back. Since we only put in like one sample, It's kind of ugly, but at least it proves that it's up and running and that we're fine. Okay. So now that we have this, let's go ahead and scale up and see what we can achieve. So I'm just going to, well, we can actually do it inside of our, we can do it right here. We go to deployment configs, actions, and let's just scale it up here. I think I can go up to 9 uh, with the current infra that I have. So let's go up to 9. And let's go ahead and check. Okay, so here you can see it has rendered all of the tiles. It's not great because we only have one sample, but that's going to change very, very soon with the power that we just deployed, right? Okay. Let's go ahead and upload it again to all of the servers. And now you can see here, you see all of the 9 instances have received the file through the broadcast that I did through this service and then the Artemis program. Let's ask all of them to open the file. So they all replied, status open. And now let's go ahead and raise the samples a little bit here. Let's put in 128 samples, divide the frame to 4 in each axis, and then send in the rendering request. Okay. So now let's just wait for the tiles to come back, and we shall soon see. I think, yeah, it takes around 15 seconds, 16 seconds per tile, and you can see them appear here in real time. So the first batch of 9 has already arrived, and now it's working on the next batch of 9 tiles. Okay, and our image is complete. So this is then in total, with the compute power that I have, it took around 20 seconds or like 30 seconds, I would say, compared to more than 5 minutes if we would have done this on a regular machine with a single CPU, right? So this is pretty great, and we can go ahead and be creative. Okay, so let's go back here. So some notable behaviors here. You can actually see that in the architecture that was presented here, there's no complex scheduling involved. There's no central scheduler, but simply by putting a queuing system and then some compute resources behind it, it kind of organically uses up all of the resources that we have on our infrastructure, which is good. So the resources are never actually sleeping. As soon as one becomes free, and if there's still work to do, it's actually doing it. So it's kind of a hungry consumer pattern that organically optimizes the usage of your resources. And this is important because sometimes you have tasks that takes more time than the others. So here, for example, you could have tiles that are more complex than others. And so they might not work at the same speeds. But if you wanted to orchestrate that centrally, it's practically impossible. So the only way to achieve that is through a queuing system and worker system like this. Right, so that is interesting. So the key takeaways from this presentation is it was really fun to do. The render farm is something that is very nice to demonstrate. But if you take the architecture, you could think of other applications for your business that can be distributed like this. So you can think of things like risk calculations, Monte Carlo simulations, AI training. So OpenShift has also GPU-based calculations that you can distribute to. And you think of this pattern in order to do so in an efficient manner. So if we go beyond this demonstration, we could actually also think about leveraging Knative platforms. As I mentioned before, we have these Quarkus services that boot up very, very quickly. So we could actually imagine scaling the workers to zero, and only when there's work to be done, they would be scaled up automatically to take on the load. And this would add to the some beneficial properties to optimize the usage of resources, and not having resources sit there waiting for work and doing nothing. Okay, all of the source code for this demo, you can find it on my GitHub link here, and I will open up for questions if there are any. And this was it for presentation today. So yeah, I hope you liked it.